In this episode, we will talk about actor-critic learning with offline data. Actor-critic algorithms are a really ingenious approach in reinforcement learning, or RL.
They really are.
They essentially get the best of both worlds by having one component, the actor, directly learn how to behave, that's the policy, and another, the critic, learn the value of those behaviors.
Right. The critic evaluates what the actor is doing. This combination has become pretty fundamental in modern RL.
Absolutely. Actor-critic methods have seen some remarkable success tackling really complex tasks.
Definitely. But a significant hurdle has always been achieving optimal sample efficiency.
Sample efficiency, meaning getting the most learning out of the fewest interactions with the environment.
Exactly. What we mean by that is learning a policy that is very close to the absolute best one possible. Technically, we call that epsilon optimal, while using the minimum amount of trial and error, so the fewest number of interactions.
And there's a theoretical benchmark for this.
Yes, the benchmark we often aim for is using on the order of $1 epsilon 2f2 trajectories or sequences of experiences. Getting that efficiency is tough.
Okay, let's break down why this is such a big deal. Sample efficiency is key, especially when interacting with the real world has cost time, resources, maybe even safety.
For sure.
Now, the challenge in reaching this 0.1 epsilon 2 efficiency becomes particularly acute when we move beyond simple scenarios and use what's called general function approximation.
Yes, using things like neural networks to represent the policy and value.
Right. These let us tackle incredibly complex problems with huge state and action spaces. But they also introduce complexity into the learning itself.
Precisely. When we use these powerful function approximators, the need for what we call strategic exploration becomes paramount.
Strategic exploration. So not just wandering around randomly.
Exactly. Think of it like trying to discover the most valuable resources in a completely unknown continent. You can't just wander aimlessly. You need a strategy to intelligently explore, to decide where to invest your limited efforts to find the best outcomes.
Makes sense.
And, many earlier attempts to understand the efficiency of actor-critic methods kind of relied on simplifying assumptions.
Like assuming you could easily get anywhere in the environment.
Yeah, assumptions about state action space reachability, or that the data we already had gave a good coverage, we'd say. They effectively sidestepped the really hard problem of how to explore effectively from the get-go.
So if we're already assuming we've explored well enough or have good data, the problem shifts to just how best to use that information, like having a map that's mostly accurate.
Right, you just need to fill in the details.
But what happens when we truly don't know what's out there? How do we actively and strategically explore to find the best path forward?
That is exactly the open problem that this research directly addresses. So this deep dive will focus on a new algorithm called Aurora.
Nora. What does that stand for again?
It's no-regret optimistic, rare-switching actor-critic. And Nora is specifically designed to meet this challenge, achieving that gold standard of sample efficiency in actor-critic learning with general function approximators, even when we need to be really strategic about exploration.
So it aims for that 0.1 epsilon 2 complexity without needing those strong starting assumptions about reachability or data coverage.
That's the goal, learning a near-optimal policy efficiently without needing those kinds of prerequisites.
All right, so Nora is our main subject. But before we delve into the nuts and bolts of Nora, the research first discusses what it terms an easy case using an algorithm called DOUA. Why start there? What's the point of this easy case and where does it fall short?
Well, the DOUA algorithm, that's algorithm 1 in the paper, serves as a really valuable starting point. It helps us grasp the inherent difficulties here. It's actually a modification of a previous algorithm called GOLF, but adapted for the actor-critic setup.
And how does it work? What's its key idea?
The key distinction in DOUEGO is that its critic component aims to estimate the value of following the current policy, let's call it DOUA, rather than directly trying to estimate the value of the absolute best possible actions, which we call TICI.
So it's evaluating its current strategy, not the ultimate best strategy.
Exactly. And it also employs optimistic planning.
Optimism.
Yeah.
Meaning it explores actions that look promising even if their current estimated value isn't the absolute highest.
Precisely. It maintains some uncertainty about action values, and that uncertainty encourages it to try things out. The way DOUA updates its policy is also interesting. It's stochastic, following a rule, equation 8 in the paper, that mathematically resembles techniques like multiplicative weights or the hedge algorithm from online learning.
Hedge. Okay, so it's drawing on established online learning principles. Now, the research mentions Theorem 1, which gives a regret bound for DOUA. What does that tell us?
So, Theorem 1 gives a theoretical guarantee on performance. It bounds how much worse the policies learned by DOUA can be compared to the best possible policy over time. This difference is the regret.
And it breaks down this regret.
Yes, into two main parts. First, there's the tracking error of the policy, how much the sequence of policies DOUA learns deviates from the single best fixed policy, $. Second is a term related to the Bellman error.
The Bellman error.
Uh,
That's fundamental in RL, right?
Yeah.
It measures how consistent the value estimates are.
Exactly. It quantifies how well our estimated value functions satisfy the core Bellman equation, which links a state action value to immediate reward plus the discounted value of the next state. Theorem 1 shows this regret is limited by factors like the episode length $, number of actions $, and a complexity measure called the sequential eluder coefficient, or SEC.
Okay, that sounds like a fairly standard way to analyze learning algorithms. But then the paper immediately flags this vacuous bound issue. It's related to something called the log covering number of the policy class. Let's dig into this. What's a covering number, and why does it cause problems here?
Right, this is a crucial point. A covering number essentially measures the complexity or richness of a set of functions, in this case, the set of possible policies the algorithm might learn. It tells us how many simpler functions we'd need to kind of cover or approximate any function in our more complex set reasonably well.
Okay, a measure of complexity.
Yes, and the policy class represents all policies the algorithm might consider over $ steps. Now, lemma 1 in the paper shows something problematic. The logarithm of this covering number can grow linearly with the number of significant updates we make to the critic.
Linearly. So every time the critic learns something new, the space of potential policies gets significantly more complex.
That's the issue. Think of it like this. Refining our value estimates opens up new plausible strategies, and this expansion can happen fast. When this log covering number grows linearly, it can make the regret bound from Theorem 1, well, huge. Vacuous, as they say.
Meaning the bound becomes so large, it doesn't actually tell us if the algorithm is learning efficiently.
Exactly. In many practical scenarios, like using linear models or even neural networks for the critic, this linear growth makes the theoretical guarantee pretty uninformative about actual performance.
That makes perfect sense. An upper limit that keeps growing isn't much of a limit. So this easy case turns out to be not so easy in many common situations. But the research then presents a good case in Corollary 1, where the bound looks much better. What makes this scenario good?
The good case happens if the function class dollars that we use for our critics has a specific mathematical property. It's called closure under truncated sums, defined in definition 3.
Closure under truncated sums. What does that mean intuitively?
It essentially means if you take a bunch of Q functions from your class dollars, chop their values off so they stay within a certain range, like 0 to h, the episode length, and then average them, the resulting average function is still within your original function class $5.
So the class is kind of stable under this operation of clipping and averaging.
You could think of it that way, yes. It's a form of robustness. And lemma 2 shows that if Lottie has this property, the log covering number of the policy class doesn't explode linearly anymore. It stays controlled, depending mainly on the complexity of $5 itself.
So if our function class f behaves nicely in this specific way, the complexity of the policies doesn't balloon out of control with critic updates. And that gives a more meaningful regret bound for DOUA 1.
Exactly.
As shown in Corollary 1.
Exactly.
But the research is quick to point out that this good case isn't always realistic. Why not?
Well, the crucial point is that many function classes we commonly use in machine learning, linear models, neural networks, decision trees, random forests, they generally do not satisfy the strict closure under truncated sums property.
Really? Even linear functions?
Well, averaging linear functions gives a linear function, but if you first truncate them, limit their output range, and then average, the result usually isn't a simple linear function anymore. Same goes for neural nets. Averaging truncated networks doesn't guarantee the result fits neatly in the same complexity class.
I see. So, while it might seem okay sometimes, the strict mathematical condition often doesn't hold for the tools we actually use.
Correct. And this limitation of the easy case really motivates the need for a more general solution, one that works without relying on this restrictive assumption about the function class $5.
Which naturally leads us to the hard case and the introduction of Nora Algorithm, the no-regret optimistic, rare-switching actor-critic algorithm. Now, the paper suggests that just taking DOUA and adding rare switching critic updates, a technique used before, doesn't solve the problem if we're still targeting what's the challenge there?
The core difficulty comes from targeting the value of the current evolving policy The critic is trying to hit a moving target. Now, if you update the critic only infrequently, the rare switching, think about the Bellman error. The error measures how well your value estimate aligns with reality. But reality is defined by the policy. The error relative to the policy when the critic was last updated, say, could be very different from the error relative to the current policy.
Ah, because the policy has changed in the meantime.
Exactly. The critic was trained to be accurate for time, but now, at time, we need optimism relative to decide how to change the policy next. This mismatch leads to insufficient optimism.
And that lack of optimism hurts exploration.
It does. Figure 1 in the paper illustrates this nicely. It can cause a tracking error relative to the optimal policy terror that just accumulates linearly over time, which means linear regret exactly what we don't want.
So the critic is chasing a moving target, updates infrequently, falls behind, and doesn't explore optimistically enough. Makes sense why just adding rare updates wasn't the full solution. Now, the research proposes a key shift. Have the critic target Q, the optimal Q function, instead of the Q. How does this change help?
This is a central idea in Nora. By shifting the critic's focus to learning the optimal Q function, Q drawer, we ensure we maintain sufficient optimism. Lemma 14 formally shows this. Now, the Bellman operator we care about becomes fixed.
Fixed, because Q doesn't change.
Right. Q is the value of the best possible way to behave. It's a fixed target. We no longer have the complication of needing to control the complexity of a policy class raised to the power of $2 like we did for DOUA. We just need to worry about the complexity of our function class dollar.
So it simplifies the complexity management significantly.
It does, because the Bellman operator associated with the greedy policy, the one that always picks the best action according to the current Q estimate, has a nice mathematical property called contraction. Managing the complexity of just phi dollar becomes much more tractable.
Okay, that sounds like a major improvement, a stable learning target for the critic. But doesn't targeting Q dollar introduce a new issue? The paper mentions the current policy might deviate from the greedy policy that's based on the current Q estimate by R. Why is that deviation a problem?
That's the next challenge, yes. Even if our critic is doing a great job approximating the optimal Q of dollars, our actual exploratory policy might still be quite different from the policy that would just exploit that knowledge.
So we might know what's best, but not actually be doing it consistently because we're still exploring.
Exactly. This difference, also shown conceptually in Figure 1, can mean we don't consistently take the actions believed to be optimal, which hurts overall performance. Nora tackles this with a clever mix of 3 ingredients.
3 ingredients. Okay, what are they?
First, as we discussed, optimism, essential for guiding exploration strategically. Second, off-policy learning.
Off-policy, meaning it can learn from past experiences even if they were generated by older policies.
Precisely. It allows Nora to reuse all historical data efficiently. And third, building on targeting Q dollars is the combination of rare switching critic updates with policy resets.
Policy resets, what does that mean?
Because the critic is aiming for a fixed target Q dollar, we can afford to update it less frequently, like in that Jiang et al. Work mentioned. This is the rare switching part. But critically, after each of these infrequent major critic updates, Nora resets the policy back to the uniform random policy.
Back to random. Why?
This reset controls the deviation from the greedy policies. By essentially starting exploration fresh after each major improvement in the critic's understanding of Q dollar, we prevent a policy from getting stuck too far away from the currently estimated best path.
I see. So infrequent critic updates let the critic get a good handle on Q, and the policy resets keep the actor from drifting too far during the exploration phases between those updates.
Yeah.
The paper also mentions UGA uses an increased learning rate for the policy. Why?
Yeah, the increased learning rate for the policy is needed to compensate for those resets. Since we periodically wipe the slate clean on the policy, setting it back to uniform, we need to make bigger adjustments between resets to make progress and catch up with the critic's potentially improved understanding of Tate dollars.
Like hitting the gas harder after stopping at a light?
Kinda, yeah. Gotta regain momentum.
Okay, that makes sense. Now, what about the guarantees? What does Theorem 2 say about Norai's performance?
Theorem 2 is the main result for Nora. It gives a regret bound of roughly dh4 log ft plus square dh5 log ft.
Okay, let's unpack that. D dollars is some complexity measure.
Right. Dollars is the delta-type Bellman eluder dimension, a measure of the complexity of the function class. $5 is the episode horizon, 8 are the number of actions, $5 the effective size of the function class, and 10 are the total episodes.
And the key takeaway from this bound?
The crucial implication is the sample complexity. This regret bound means that O1 epsilon 2 trajectories, roughly speaking and hiding some polynomial factors in dh and log terms, are enough to learn an epsilon optimal policy. And importantly, this holds under fairly general conditions, without those restrictive assumptions on $5 or data coverage that limited earlier work.
That's really the headline result then, achieving optimal epsilon 2 sample complexity with general function approximation without strong prior assumptions. You mentioned a delta-type Bellman eluder dimension. Assumption 3 in the paper relates to this.
Yes, assumption 3 basically posits that the function class ballers we're using for the critic has a bounded delta-type Bellman eluder dimension. This dimension is a specific way developed in prior work to quantify function class complexity in the context of RL, generalizing things like Bellman rank.
And assuming it's bounded is important for the math.
It's critical for the proofs. It lets us control the errors in function approximation and figure out how much exploration is needed to get the regret and sample complexity bounds stated in Theorem 2.
Got it. The research also draws an interesting parallel between Nora and DDPG, deep deterministic policy gradients. What's the connection?
Yeah, there are some interesting conceptual similarities. DDPG is a popular algorithm in deep RL, especially for continuous control. One similarity is that DDPG also effectively tries to learn an approximation of $T using a target based on the current policy.
Okay.
And DDPG famously uses slowly updating target networks for both its actor and critic. This stabilizes learning and is conceptually quite similar to the rare switching critic updates in Nora.
So the idea of stabilizing the value target and updating less frequently appears in both, though implemented differently.
Exactly. While DDPG typically uses a deterministic policy plus noise, the core idea of stabilizing the value learning target shares common ground with Nora's design. This connection suggests that the theoretical insights from Nora might help us better understand or even improve practical deep RL algorithms like DDPG.
That's a fascinating link. Now, the research then broadens its scope to consider hybrid reinforcement learning. What exactly is hybrid RL in this context, and what are its advantages for actor-critic methods?
Hybrid RL is where you have access to two kinds of data: pre-collected offline data, maybe gathered for some other purpose, and the ability to collect new online data through interaction.
So using both existing data and new exploration.
Right. And for actor-critic methods, this hybrid approach offers two main potential benefits. First, leveraging offline data might give us computational efficiency gains. If you have a good chunk of relevant offline data, you might be able to reduce or even skip the explicit optimism needed for exploration in purely online settings.
Making the algorithm simpler or faster.
Potentially, yes. Algorithms 3 and 4 in the paper explore this idea. Second, by smartly combining offline info with further online exploration, we can aim for sample efficiency gains, learning better policies faster than with either offline data alone or just online learning. That's the focus of Algorithm 5.
So offline data give a head start, maybe reducing exploration cost, and we can still fine-tune online. Algorithms 3 and 4 are examples without optimism. How do they work?
Right. Algorithms 3 and 4 are designed for the hybrid setting without online optimism. Both use rare switching critic updates. Algorithm 3 is like DOUA, targeting on. Algorithm 4 is like Nora's core, targeting $Q.
And they use both data sets.
Yes, they combine the offline dataset with the online data when they update the critic using fitted Q evaluation, FQE.
Okay. And how do we analyze these? There's a new concept mentioned.
Yes, to analyze these, the paper introduces the single policy concentrability coefficient. Defined in definition 4, it basically measures how well the state action distribution under the optimal policy dollar is covered by the data distribution in the offline dataset deployers.
So how relevant is the offline data to the optimal behavior?
Pretty much. Theorems 3 and 4 then give regret bounds for algorithms 3 and 4. These bounds include an extra term, depending on this concentrability coefficient and the size of the offline dataset.
And the implication.
The key result is that if you have enough offline data, specifically null or all on the order of 2, you can still get score 2 regret and 1-on-2 sample complexity, even without online optimism. This addresses some limitations in earlier work.
That's quite something, achieving optimal sample complexity in hybrid RL without online optimism, just relying on good offline data coverage. Now, Algorithm 5 is the hybrid version of Nora itself. How does it combine the data?
Algorithm 5 takes the core Nora ideas optimism, targeting $Q, rare switching, policy resets, and extends them to use offline data. It does this by simply adding the offline dataset dollar to the online data when it constructs the confidence sets used for optimistic exploration in the critic updates.
So the optimism benefits from both data sources.
Exactly. And to analyze this, the paper introduces the partial all-policy concentrability coefficient in definition 5. This considers partitioning the state action space into an offline region, sexavarsion, and an online region, sexadollar, where we rely on online exploration.
Okay, partitioning the space based on data coverage.
Yes, and the UM5 gives the regret, bound for hybrid Nora. What's really neat is that this bound effectively optimizes over all possible partitions.
Right.
Meaning, if the offline data provides good coverage over a large chunk of the important state action space, the overall regret can be significantly lower than in the purely online case. The need for exploration, captured by the sequential eluded coefficient term, is reduced because it only applies strongly to the potentially smaller section region.
So hybrid NORA really adapts to how good the offline data is, potentially speeding up learning dramatically.
That's the idea. It shows the clear potential for sample efficiency gains by smartly combining offline and online data within NORA's optimistic framework.
Okay, finally, the research includes numerical experiments. What were the key takeaways there?
They ran two main experiments. First, they looked at optimism in linear MDPs, comparing algorithms 1, DOUA, and 2, ORA, against a version of LSVI-UCB, a known efficient algorithm for linear settings. They used a linear Tetris task.
And the results?
Interestingly, in that setting, where the conditions for algorithm 1 were mostly met, they didn't clip Q functions, which helps satisfy that closure property we talked about. Algorithm 1 actually performed really well, even better than LSVI-UCB initially. Algorithm 2, NORA, also showed the expected sort-to-regret scaling, though it was a bit slower at the start.
So DOUA works well when its conditions hold. What about the second experiment?
The second one was on hybrid RL using a challenging benchmark called AntMaze Medium Diverse V2. They compared hybrid versions of algorithms 1 and 2, 1H and 2H, against CalQL, a state-of-the-art hybrid RL method.
And how did hybrid NORA 2H do?
Algorithm 2H, which uses approximate optimism, performed competitively with CalQL. It actually outperformed CalQL in the evaluation phase, showing better initial exploration even though CalQL uses explicit pessimism and 2H doesn't.
That's quite promising empirical evidence for these hybrid actor-critic approaches.
Yes, it suggests they are practically viable and effective at using both data sources.
Okay, bringing this all together, what are the main conclusions from this deep dive into this research?
Well, in summary, this work really tackles a major open problem in online RL. It gives us ORNARA, an actor-critic algorithm using general function approximation that hits that optimal 1 epsilon sample complexity and gets score a regret.
And crucially, without needing strong assumptions about reachability or data coverage.
Exactly. That's the big step. And it achieves this through that novel combination: optimism, off-policy learning, targeting Q with rare switching updates, and those strategic policy resets.
Plus the extension to hybrid RL, showing how to potentially get even better performance by using offline data.
Right, demonstrating gains in both computational and sample efficiency in that setting.
And looking ahead, what are some exciting future research directions this work points towards?
The authors mention a few. One is looking deeper into incorporating exploration bonuses, like those used in other optimistic RL methods, into the NORA framework. Another is exploring if policy optimization can achieve mini-max optimal rates in linear MDPs, building on recent work.
And practical application.
That's key. A crucial area is figuring out the practicalities of applying NORA with very complex function approximators like deep neural networks. How best to tune it, adapt it for really high-dimensional problems that will be vital for realizing the full potential here.
This has been an incredibly insightful exploration. The development of NORA and its hybrid extensions really feels like a significant step forward in making reinforcement learning more data efficient and capable of effective exploration.
It really does. These advances, both theoretical and the promising empirical results, help pave the way for building more efficient, more robust AI systems, ones that can learn effectively even when data is limited, and strategic exploration is absolutely critical.
Which leads us to a final thought for you, the listener. How might these advancements in actor-critic learning, particularly the ability to achieve optimal sample efficiency with strategic exploration, impact the development of AI systems in real-world scenarios? Think about areas like robotics, healthcare, or resource management, where data is often expensive or hard to get, and exploring safely and effectively is paramount. What new possibilities might open up?